All right, let's get right into it. If you think about it, chemistry has its own language, right? And at the very heart of that language are chemical equations. You can think of them as a kind of secret code that tells the story of how stuff, well, how it transforms. And today we're going to crack that code. So every single chemical reaction, I mean everyone, can be boiled down to a simple sentence. It's kind of the most basic way to tell the story, you know? It just lays out what you start with and what you end up with. Take this for example. When you burn a magnesium ribbon, the story goes something like this: magnesium plus oxygen becomes magnesium oxide. It's just like a recipe, really. On the left, you've got your ingredients, which chemists call reactants, and on the right, you've got your final dish, the product. Now you can imagine writing out full sentences for every reaction would get old pretty fast. So chemists came up with this awesome universal shorthand using chemical formulas. It's way faster, super clear, and anyone anywhere in the world can understand it. So our little recipe now looks like this: Ming plus O2 arrow, MGO. See? Simple, elegant, and really powerful. But there's a catch. Of course, there's a catch. Just because this recipe is short and sweet, it doesn't mean it's telling the whole truth. Yeah, there's actually a hidden problem here that we need to figure out. So let's put on our detective hats for a second. Does this equation actually add up? I mean, is it really telling the truth? To find out, we have to do something absolutely crucial. We need to count the individual atoms on each side of that arrow. Okay, check this out. On the left side, the ingredient side, we're starting with one magnesium atom and two oxygen atoms. Got it? But now, look at the right side, our final dish. We've got one magnesium atom, but wait, only one oxygen atom. Whoa, hold on a second. What just happened? An entire oxygen atom has just vanished? It's gone. Our neat little equation is basically telling us that matter just disappeared. And that? Well, that's just not possible. It literally breaks one of the most fundamental rules of the entire universe. And this brings us to one of the most important principles in all of science. I'm talking about a law that governs everything from, baking a cake in your kitchen to a star exploding light years away. And here it is, the law of conservation of mass. It states that mass can neither be created nor destroyed in a chemical reaction. What does that actually mean? Well, it means the total number of atoms for each element has to be the same on both sides of the equation. You can't just lose an atom along the way. It's impossible. So that simple equation we had, Mg plus O2 goes to MgO, it's scientifically wrong. It's what we call a skeletal equation. It's just a draft. It's unbalanced. To make it right, to make it actually obey the laws of physics, we have to fix it. We have to balance it. And that is exactly what we're going to do right now. It's a really cool step-by-step process, almost like a puzzle, where we adjust the recipe until every single atom is perfectly accounted for. All right, let's tackle a new one, something a little more complex. This is the reaction of iron with steam. Right now, as you can see, it's totally unbalanced. So let's fix this thing together, one step at a time. Okay, so step one, a good rule of thumb is to start with the most complicated looking thing, which in this case is the Fe3O4. See how it has 4 oxygen atoms? Well, over on the left, our water molecule only has 1. That's a pretty big imbalance, so that's where we'll start. Now, here's the most important rule of the game. We can't change the formulas. We can't just write H2O4 because that's not water anymore. The only thing we're allowed to change is the number of molecules. So we do that by putting a big number called a coefficient out front. By putting a 4 in front of H2O, we now have 4 water molecules. That gives us 4 oxygen atoms on the left, and just like that, our oxygen is balanced. 4 on the left, 4 on the right. Boom. But look what we just did. By fixing the oxygen, we've kind of messed up the hydrogen, haven't we? We now have 4 times 2. That's 8 hydrogen atoms on the left. But over on the right, we've still only got 2. Okay, no problem. Time for step 2. And we fix the hydrogen the exact same way. We just pop a 4 in front of the H2 on the right side. Now we have 4 times 2, which is 8 hydrogen atoms. And bam, hydrogen is balanced too. See how this works? We're so close, just one element left to go. On the right side, in that Fe3O4, we have 3 iron atoms. But look at the left, We've just got one lonely iron atom sitting there. This is the final piece of our puzzle. This is the easy part. To balance the iron, we simply put a 3 in front of the Fe on the left, and we're done. Let's do a final count just to be sure. On the left, 3 iron, 8 hydrogen, 4 oxygen. On the right, 3 iron, 8 hydrogen, 4 oxygen. It's perfect. Our recipe is now 100% in line with the law of conservation of mass. Okay, so our equation is perfectly balanced. Now we can add one last little layer of detail to make it even more useful for a chemist. Chemists use these tiny little symbols in parentheses to show the physical state of everything in the reaction. Pretty straightforward. S for solid, L for liquid, G for gas, and AQ for aqueous, which is just a fancy way of saying it's dissolved in water. So our final, fully dressed up equation looks like this. Now we can see the whole story. Solid iron reacts with water in its gaseous state, steam, to produce solid iron oxide and hydrogen gas. It's this level of detail that makes chemical equations such an incredibly powerful tool. Alright, we've cracked the code together, but now the real test is seeing if you can do it. So here's a challenge for you. Hydrogen plus chlorine becomes hydrogen chloride. Your mission, should you choose to accept it, is to first write out the skeletal equation with the right formulas and then use everything you've just learned to balance it. Go on, give it a shot.